There you are. That's y'all, right?
Yes. Thank you.
All right, so I want you to tell me what the products are for these reactions. Okay, why don't I have an arrow? Wait. It's like popping up. How to get that to go away. Okay, so what do you get from this first one, you guys? That plus ethanol, H+. What do you get? Here is your clue. What am I going to get?
I feel like this is a trick question.
It's not a trick question. I don't think.
Positive.
I'm positive. I lost an electron.
I have an OA over.
Nope.
And then C.
Okay, you get that, but it doesn't stay there. The next one reacts. Okay, so you end up losing water. So you do form that, but you get the ketal, not the hemiketal. Okay, but we're going over it.
Yeah.
That's a T, and that's an A, and the world doesn't want to write right. All right, so what do you think you get from them? Yeah, okay, so can you draw it?
Like an oxygen, another oxygen, then a C, and then the two. Oh yeah.
Some students nicknamed it the BART reaction of years.
Oh, I see that now.
I thought I get you.
Is that going to help you remember? I don't know, but I'm trying it. All right, what about this one? Can you do this one now? What are you going to get?
The same thing. So.
Bart's just going like that. You could make him straight. I just didn't. I was afraid I wouldn't have enough room. Okay, we feel a little better about it? Okay, good. Okay, typically hemiacetals are unstable except for cyclic. So here we have an aldehyde and an alcohol in the same compound. Okay, and what will happen is that alcohol, the lone pairs will go there, you'll go out to the O, and then you'll end up protonating it, and you have a cyclic hemiacetal. Okay, these are stable. Okay, now where do you see these? Does anybody know? Does anybody study sugars? Any of your biology classes? Have you talked about glucose? Maybe. Okay. The sugars make hemiacetals. They have a straight chain form and they have a cyclic form. And all I'm going to do is show you glucose because that's kind of the basic one. But here is D-glucose. In a Fisher projection, all those C's would just be crosses. And remember what that means. That means that the sides are coming out at you. Okay? This is not the most stable, but it is a convenient way to grow. Okay, so what will happen is look at 1, 2, 3, 4, 5, 6. Okay, this is your 6th atom in your 6-membered ring. Remember that 6-membered rings are kind of magical. 6 and 5 want to form really easily. That's a 6. It's looking like. Okay, so here it is. And what this is that, oh, here, the orange O. They're all color-coded. I stole it from Con. All right, so because I didn't have time to make it. So those lone pairs go to that C, you go out to the O, and then it will pull off that proton. And this C right here, the red one, here we'll put a little star, is this one, the red one, okay? And this is how you get, have you heard of alpha D-glucose and beta D-glucose? This is how you get the 2 forms. When it cyclizes, the OH can form up or it can form down. Beta up, alpha down. Okay, beta up, alpha down. And then all these, it's like taking this whole molecule, putting it like that, and it's kind of making the little ring because all these are going back, remember? These are all coming out. So you pick that up, put it sideways, and that's how you end up getting this. Okay, so all of the hexoses, the ones that have 6 carbons, can do that. Okay, and these are the main forms of glucose. So do you know that there are things made out of glucose that we can eat? But there are also things made out of glucose that we can't eat because of the way the glucoses are hooked together. They can have a beta linkage or an alpha linkage. And it's really interesting how, because of how it looks, our enzymes can eat up some of them and some of them we can't. Okay, so you probably talk about that in biochem. Let's put it this way. I hope you talk about that in biochem and cell and molecular and all those good classes where you'll go into all those. Okay, I just wanted to show you because this is your stable form. Okay, now you remember what the big D means, right?
On which side the OH?
On the last chiral center, yes. And you always draw them in this way with the aldehyde at the top and the CH2OH.
So you said that's a stable.
Yeah, this is going to be nice and stable, even though it's a hemiacetal, but because it's a ring, that makes it stable. Yeah. Yeah, it like kind of wants to do that because it's intramolecular within the mouth. Okay. I'm not going to make you draw any of them. I just want you to know about it. Okay, so what is the structure of the major organic product from the following reaction? Let me get something other than black for some reason. Only 13 today
I think we have some scramblers.
on the paper.
Well, and Endgame came out.
What?
Oh yeah, I guess Endgame did too. Endgame went out.
Endgame. Is that the Avengers movie?
Yeah.
Oh.
I don't watch that.
My daughter and her husband went to see it at 10:30 last night. And y'all, they get up at 4:30 in the morning to go to 5 a.m. CrossFit. And they went and taught at 10:30 last night. I'm like, are you crazy? I guess you must be young. Is that it?
Don't tell me.
I heard it was long too. All right, I only got 12. Shouldn't I have 13 or can I not count today either? Okay, cool. All right, yes, it's A. Woohoo! Okay. Why isn't it C? Right. because this intramolecular reaction will happen much faster than something that would make that. Okay, why isn't it B? Because that's just wrong. Why is it D? That's just weird. Okay. Just saying. All right, I've already mentioned this, but acetals and ketals are stable in neutral and basic conditions, but they decompose in acidic condition. So here is a ketal, and if you add water and a lot of acid, almost like an equivalent of acid, typically what ends up being used, you end up going back to the carbonyl compound. Okay, so because of that, we use them as protecting groups. Protecting groups are things that hide a functional group, and so it doesn't react, and then you can get it back later. So here's an example. Let's say you want to take this compound and you want to add NaNH2, so you get the C minus, and then add methyl iodide and put a methyl there. Pretty simple thing. But you can't do that with the carbonyl there. The carbonyl will react with your base. Okay? And remember that when you make these things, I'll just do that, they add to the carbonyl. We don't want to do that. We don't want that to add to another one and maybe make a fancy compound. Okay? We want to just put that methyl group on. So what do? Here's what we do. Maybe. Okay. So we are going to put on a protecting group. Remember, when you put this on, you do not use a full equivalent of acid. It is catalytic. So it's going to be like 1%, less than 10% for sure. Okay, and you'd probably use H2SO4 just to help, you know, keep things from adding to that triple bond. And we put on a protecting group. So we did the BART one. So now this is no longer a carbonyl, it's a ketal. This is now a ketal. Okay, so we're going to add NaNH2 and ammonia, liquid ammonia, remember? And we're going to pull off that proton. And then we're going to add our methyl iodide, and we're going to methyl. Okay, then we're going to add water and acid, and sometimes they even heat it up a little bit. You got to be a little careful because we don't want to add across that triple bond. But, and that will probably affect your yield. You probably wouldn't be as good. But you can do it. So you can remove that and get your carbonyl back. So notice that we regenerated the carbonyl. So we were like being sneaky. We were just doing a little sneaky stuff. Okay? Organic chemists have worked very hard at being sneaky. Did you notice that? Okay, this is a compound called a Wittig reagent. It's German. The guy was German that came up with them. And he used this thing called a triphenyl phosphonium ylide. Okay, they're generally referred to as ylides. Okay, I have no cute thing on how they came up with that name. But you can see where the triphenyl phosphine part is. Okay, and you have a plus minus in there. It can be drawn the way it is up there, or it can be drawn like this with a double bond. Okay, so it could be drawn either way because remember that phosphorus can break the octet. Okay, the bane of the chemistry student, breaking the octet. Okay, so we would take an aldehyde or a ketone, and look what we made. Okay, notice what happened. The O is now where? At the end, it's on the phosphorus. There it is, okay? And this part of the molecule is here. So we made an alkene that's real unique, okay, basically, depending on what A and B are. Okay, to make the Wittig reagents, they will take triphenylphosphine plus an alkyl halide and then throw in N-butyl lithium. Okay, and butyl lithium is a super strong base. Super duper base. Okay, what is the conjugate acid of N-butyl? Okay, so here is butyl lithium. Okay, what is the conjugate acid of butyl lithium? What do you do to figure it out? You remove the lithium, and what do you put there? A hydrogen, right? Okay, so what is that? Butane. Do you think of butane as being an acid at all? Please say no. Okay, so I don't have to cry. Okay, that's right. So that tells you how strong a base this is. Okay, it's super strong. Right? Remember, if you don't know, sometimes it helps to look at the other one, the conjugate. Okay, so here is our phosphorus ylide, and here they drew it with a double bond, and A is a hydrogen and B is a metal. Okay, and here is our compounds. So we have this compound up here, which is what? What's the name of that? Yeah, acetone. Just checking on you, making sure you're awake back there. Okay, so what am I going to get? Okay, what's going to be gone from the acetone? The O, and then what are we going to have? The green part's going to be on there, right? So we're made an alkene, okay, with 3 methyl groups on it. Okay, what if we did this one? This one is cyclohexanone, and we're going to add this ylide. Okay, so what are we going to get? Or cyclohexane, and what's going to be on it? The double bond to this C, right? The mechanism is real straightforward. It's a 2+2 cycle addition, and it's concerted. Okay, so what does all that mean? What does the concerted part mean? Happens at one time. Okay, what do you think the 2+2 is? Where did we see numbers like that before? What kind of reaction? What was the reaction? Diels-Alder, and it was a 4+2, right? Okay, so what were the 4 and what were the 2? They were what electrons? The pi electrons, right? Okay, now we're doing a 2+2. So we got pi electrons here, and we got pi electrons here, okay? Because you can draw it like this, all right? So, but the easier way to do the mechanism is to think that C is negative. So it's going to go to the carbon of the carbonyl, and then what's going to happen is that's going to go to the P. Okay, oxygen and phosphorus have a little elemental love affair going. Okay, they make super strong bonds and they love each other. And that is really the driving force for this reaction, because once you get your little cyclic ring here, it falls apart. Okay, and when it falls apart, the P and the O stay together because they love each other. Okay, so this is your nice stable bond. Okay, and those can easily be separated from the other thing. Okay, so it's really the overall mechanism is going to be 2 steps. One step is going to be the 2+2 cycle addition, and the next step is it falling apart. Okay, don't worry about the mechanism to make the ylide. Okay, the Wittig reagent. All right, you got it? Pretty straightforward. Somebody had an article about Wittig reagents. Who was that? I don't remember. I just remember somebody did because I remember looking at it. Okay, so what is the major organic product for the reaction below? you think you're gonna get? Practice for the test. Okay. Yep, it's C. I think you got it. Okay, so we're going to lose this. That's going to end up on this. Okay, so you're going to get okay, and this are going to make that double bond. Okay, we got it. Notice that you always get the double bond to the carbon. The phosphorus goes with the O. Okay, remember they love each other. I'm telling you that to have you remember that. Okay, this compound up here is a carbonyl compound, and it has a double bond conjugated to the carbonyl compound. Okay, all right. But we're looking. Well, that made me worried. Okay, it is referred to as an alpha beta unsaturated carbon. Okay, just like when you do that nomenclature for those carboxylic acids that uses the alphas and the betas, that's where it comes from. So if you had a beta gamma unsaturated, it would be between here and the next carbon. Okay, that's all. But those don't make any difference because this is conjugated, and that's the whole big deal, is it's conjugated. Double, single, double. Okay, you can draw resonance forms for it. One is where you just take the pi electrons in the carbonyl and put them out to the O. Why do we go out to the O and not to the C? The oxygen is more what? Electronegative. Okay. So that gives us this resonance form. But you can do another one because it's next to the double bond. And so you would also get that resonance form. Okay, so there are two different ones. Notice that there are two spots that are electrophilic. Two spots that got a plus on them. This spot and this spot. Okay, so if you're a nucleophile and you're going to come in here, okay, to this molecule, you got two possibilities. You can go to the beta carbon or you can go to the carbon of the carbon. How negative you are will vary which site you go to. Okay, so when the nucleophile is a very strong base, examples of that are Grignard reagents. Okay, y'all remember those, right? MgBr or MgI or MgCl, but R. I'll write R, MgBr. Those are the ones we did the most. Okay, a hydride ion. Where would you get a hydride ion from? Lithium aluminum hydride, sodium fluorohydride. Okay, alkyl lithium. Those are things like that, and butyllithium that was in that other example. Okay, so I'll just give you methyl lithium. Okay, so when those react with alpha beta unsaturated carbonyl compounds, they go to this site, the carbon of the carbonyl. Okay, this is generally under kinetic control. So what does that mean? Remember kinetic, thermodynamic. What was kinetic? Formed faster. Thermodynamic is more stable. Good. Okay. It's irreversible, but I'm not worried about that. Okay. And then something would protonate that O, and looky there. We made a little alcohol thing. Okay, all right. Now, if you have a weaker base, okay, examples of that are going to be halide ions, chloride, bromide, cyanide ion, that's CN minus, a thiol, an alcohol, an amine, and a Gilman reagent. Do you remember what that was? The copper thing. Okay, so if you had, it usually is R2CuI is a Gilman reagent. Okay, those things are going to be under thermodynamic control, and they're going to go to the beta carbon. Remember, this is the alpha carbon, this is the beta carbon. My poor little alpha looks like it's seen better days. I guess maybe I should, that doesn't look right either. I don't know. Oh, that. Okay, so it's going to go there, and then when your nucleophile comes in, what happens to these electrons? They are going to end up being stabilized by the oxygen. Okay? They're going to end up being stabilized by the oxygen, and then it'll be protonated. And do you remember what this is? An enol, which will tautomerize to the keto form. Remember that? Way back in the dark. It all comes back. I'm telling you. Okay, so conjugate addition is always the thermodynamic product. It is the most stable product because it contains the more stable carbonyl. Okay, so look for weak bases, strong bases. Okay, strong bases react at this carbon, weak bases react at that carbon. Okay, all right, so I think I got some. All right, so what do you think you get from this one? So we have methyl magnesium bromide followed by adding ethanol. Okay, so what will be our nucleophile? What do you think? Is it the ethanol? Just the methyl, right? Because it's a Grignard. Does everybody recognize that? Okay, where is it going to react? What are the two possibles? It can react here or it can react there. Do you see that this is not a possible spot? Okay, because if you do that, you get you down at least to a 50-50. All right, so what is your nucleophile going to do? It's going to go to the, which one? The top one. Okay, you go out to the O, you get your tetrahedral intermediate, and then it's going to get protonated with ethanol. So you're going to get that, which you can then go on and do other things with. Okay. All right, what about this one? What kind of reagent is that? It's got copper in it. Okay. So what one is it? It's one of the Gilman reagents. That help? Okay, so where is it going to react? The bottom one. It's going to go here. That'll go there. We'll go out to there. The O minus will get protonated. It'll be an enol, and it'll tautomerize to the keto form. Are you sure? I hope so. Notice that the double bond is gone.
Why do you only use one of the?
You can, the other one went and reacted with another methyl. So when you actually did it, it would be 2 to 1. You would like plan that, yeah. Yeah, in these, remember, we tend to ignore balancing until you have to figure out your yield and you go. If you notice that, okay, feel okay about it? All right, so what do you think is the major organic product for the reaction below? What do you think you'll get from that? Ooh. I hope. You don't want me to just save them for the test? Or do you? Got you back to pen. All right, we all make a guess? Or an educated guess?
I was worried for today.
Why is it D?
It's D because it's an alcohol base.
Yes, because it's a weak base. That's why you don't get the ketal. Okay, you actually add to the beta carbon. Okay, so look, I'm going to go back. Look, alcohols. Okay, add to the beta carbons. Okay, what do you think happened on this one?
So why, what's the difference between that reaction and like this mechanism? Because it's using the same.
Right, but we have an alpha beta unsaturated carbonyl that has changed it. Those other ones were just regular carbonyls. They were just ketones or aldehydes. But these have this double bond.
Okay.
That's what makes it different. Okay, that's what makes it different. Okay, so what are you thinking? Okay, so what did you draw the product? Take a stab at it, and we'll see how you do. The best way to do it. Make sure you're starting to get it. I'm trying to make you try, because I'm like that. All right, looky here. Is that what you got? The bromide went to the beta carbon. Okay. Okay, what do you think about that one? The next one. What are we going to get? We're going to go to this carbon instead of this one, because this carbon, because we're using hydride, which is a strong base, it's going to go to the carbonyl carbon. Okay, what do you think about the bottom one? Yep. Okay, just takes a little practice. I think you get some in the homework. Okay. Okay, the Bayer-Villiger oxidation was done by Bayer and Villiger. Y'all are so good. Okay, now I want you to notice what that reagent is. Is that reagent in carboxylic acid? No, what is it? Oh, it's a per acid. And we used them once before, back in the dark ages. What did we use them for? You remember this? Yeah, what did we make? Epoxides. You remember that? Okay, we're good. It's all right. I'm trying to make you review too because we got that final coming up in a week or so. Okay, so what we're going to do is our peracid is going to add to the carbonyl carbon. Okay, so what will happen is this O right here, I'm going to try to color it blue, is going to end up here. Okay, so what has to happen? Well, when this adds to the carbonyl carbon, you're going to get all right, I'll just put the R's. That's 2. Oh, my gosh. Okay, so now what do we have on this O? We have 3 lone pairs, right? So what happens is when these electrons come down, they push one of these over here, and that goes there. See it? I may have it on another slide. Okay, that's all right. Then I'll just go over it again. Okay, so notice what the R prime did. It migrated. Okay, where did we see migration before? When we were making carbocations more stable, right? And we moved hydrides and we moved R groups, R minus, and fancy things like that. Okay, so it's very similar, except we don't have a carbocation. Okay, and this time, the migratory aptitude, tertiary migrates better than secondary, than primary, than methyl. Which is kind of nice because that parallels carbocation. It's like, we'll take that. That makes us happy. Okay, so notice that here in this example, the 2 R groups are the same. So it doesn't matter which one you migrate to the O, right? But down here now, they're not the same. We have a methyl and a T-butyl on either side of that ketone. And so what will happen is the T-butyl will be the one that migrates because it is tertiary. And they figured a lot of that out just by running the reactions and figuring out, well, that one moved, that one didn't move, you know, and how do you figure out which one moved? You look at the NMR. How we do it. All right, so let's see if the next slide is indeed the mechanism. No, it's a little more practice. All right, so I colored the O that's going to end up in the ester pink. Okay, so it's pink. So what do you think, which group do you think is going to migrate? The cyclohexane or the methyl? Which one do you think is going to migrate to give you your major product? The cyclohexane, why? No, it's not tertiary. It's secondary. Right? Right? 1, 2, and an H. The group that's moving. Were you counting this carbon? Yeah, don't count it.
Okay.
Okay, because it's in the carbonyl. The group that's migrating is everything else, y'all. It's going to be all of this, and there's an H there. Okay, or it would be all of this. So look at just those 2 groups. All right. Look at that. Put that right there. All right. So can you draw the product? And look at their yield. 97%. That's amazing. What do you think about the next one? Okay, you have to circle the groups that are migrating. We've got a choice between this one and this one. Okay, which one do you think is going to migrate? The one on the left, because it is secondary. Okay? And I want you to notice that the carbonyl carbon was up over here. Notice that the O is up over there, okay? We migrated and kept our stereocenter the same. That's called retention of configuration, when it stays the same. So it migrates with retention of configuration. Okay, just don't like me. Okay, so the reaction is called stereospecific. The stereochemistry of the starting material is the same as the stereochemistry in the product. Okay, if this was flipped, if this was down here, it would have stayed that way. Okay. All right, so here's the mechanism. I knew I had it somewhere. Okay, so the first thing we did was this went to here and out to the O, and then we did a little proton transfer. That's where that is. You can do that in 1 step, 2 steps. I'm not like super concerned about it. Okay, this is the big step right here. We go down, and this is migrating, and then this is leaving. Okay, the R group is migrating with its pair of electrons. Because it's got that pair of electrons with it when it migrates, that's how come the stereochemistry remains the same. This is just a proton transfer. Okay, so you see how we ended up down here. Okay. Only difference between this and what I showed you originally is that the proton transfers are. The other thing is just the nitty-gritty. Okay. All right, so look at this one and figure out what you're going to get. The perbenzoic acid is one that gets used a lot in this reaction. You can use a variety of per acids, but the perbenzoic acid, I've noticed it. Did you get it? Okay, 13. I think I need 14. Yeah, there we go. My number now. Okay, so the two groups that are going to migrate are going to be either this one or this one. This one is, and this one is primary. Who migrates better? Tertiary, so it's going to be A. Okay, now we'll tell you this. You have to remember that you make an ester in that one of the groups migrated. Okay? Does everybody see why it ain't this? Everybody see why it's not this? Like I truly made those up. Okay? The choice is really between these two. Okay? And tertiary migrates better. Okay? It's called migratory aptitude. Okay, so this is our next thing, but I'll talk about this on Monday. What you're going to do now is you're going to do your course evaluation, because I have to do them. Okay, because that apparently is late. Oh, hang on. Let me stop this.